In this lesson, we're going to be looking at the effect of changing surface area on the rate of a reaction. Now, before this, we've already spoken about collision theory, and we've spoken about the effect of changing temperature on the rate of reaction and the effect of changing concentration and pressure on rate of reaction. And we need to make sure we're able to justify these effects using collision theory. So when we're talking about surface area, we're talking about reactions where one of our reactants is a solid. Okay, so this only refers to solids. So if you don't have any reactants that are solids, then surface area isn't going to be applicable. Much like if you don't have any aqueous solutions, then concentration's not going to be relevant. And if you don't have any gas reactants, then pressure is not going to be relevant. So if we have one of our particles or one of our reactant particles that's a solid, then surface area has an effect on the rate of reaction. So what we're looking at here is a setup that would allow us to measure the rate of a reaction and vary the surface area and observe the effect that changing that surface area has on the rate of reaction. So the actual reaction is marble chips reacting with hydrochloric acid. Now marble chips are calcium carbonate. So the reaction that's actually occurring here is calcium carbonate reacting with hydrochloric acid. And we should remember from topic 4, the acids and bases topic, that when a metal carbonate reacts with an acid, you get a salt, you get water, and you also get carbon dioxide. So the salt that would be produced from calcium carbonate is going to be calcium chloride, because remember the metal from the base combines with the anion from the acid. So we're going to get calcium chloride, which is CaCl2, and we're going to get water, and we're going to get carbon dioxide. And because we've got two Cl2s, we're going to need 2 HCl. So this is the reaction. And this is a solid, which is precisely why surface area is relevant. This is aqueous, calcium chloride is aqueous, water is a liquid, and the carbon dioxide is a gas, which is precisely what we're going to be measuring. Now this setup is all about measuring the volume of gas produced over time. Now remember, whenever you're looking at rate, you're looking at the amount of product produced over time or reactant used up over time. So the first thing I would always look for in a reaction is, do we have a gas product? If so, then if you could collect the volume of that gas over time, then you're going to be able to work out rate. The other thing you could potentially do here is, because we have a gas product but we have no gas reactants, this overall reaction would appear to lose mass. So we could measure change in mass over time. But as you can see, we're measuring volume of gas over time. So we've got a conical flask, bung, delivery tube, and an inverted measuring cylinder filled with water, and we're just going to measure the volume of gas. And if we read the method, we're going to read the volume every 20 seconds for a total of 180 seconds. And then we're going to repeat the experiment, and we're going to use the exact same mass of marble chips, just different sizes. So large chips, medium chips, small chips. So we're using the exact same amount of calcium carbonate, we're just varying the surface area by using large chips, medium chips, and small chips. So we should be able to see the effect that changing that surface area has on the rate. The things we need to keep the same, our control variables, are going to be the things that could also affect the rate, and they are going to refer mainly to the hydrochloric acid. We need to make sure we're using the same concentration of hydrochloric acid each time, we're using the same volume of hydrochloric acid each time, and we've already specified we're going to use the same mass of marble chips each time. We're just going to vary their surface area. So another thing we could have done potentially is, we could have, instead of using this inverted measuring cylinder, we could have used a gas syringe. Either one would allow you to measure volume of gas over time. Obviously the timer is not shown in the diagram, but obviously there would be a timer. So if we have a quick look at the results table, now we have here the results table. So we've got volume of gas collected after 20, 40, 60, 80, 100, 120, 140, 160, 180 seconds. And then we're going to repeat the experiment for the small marble chips, the medium marble chips, and the large marble chips. So I'm just going to grab some results, because obviously we can't do this practical. So we're going to have to look at some sample results. I'll just fill that in very quickly. So we'd expect, if we were using small marble chips, 10, 20, 27, 34. This is the benefit of doing the same experiments year after year, is that you do have results ready. And then if we did that with medium marble chips, what we would see is slightly lower volumes of gas at each of the intervals, which is precisely what we'd expect, and we're going to be able to explain it in a minute. 35, 37, 39, 40, and what you notice is they both end at 40, and that is because we're using the same amount of calcium carbonate. So what I would see here, the fact that this ends at 40 and doesn't get any higher, this is the moment at which the reaction has stopped. The reaction doesn't end at 180 seconds. The reaction for the small marble chips ends after 120 seconds, because that's the point at which the dependent variable stops changing. That is an indicator that the reaction has finished. And the amount of carbon dioxide that is being produced is determined by the amount of reactant. So what that is telling us is that after 120 seconds, at least one of the reactants, either the calcium carbonate or the hydrochloric acid, has run out and the reaction is now stopped. Now, because with the medium marble chips it is slower, it takes longer before one or both of those reactants has run out. So it takes longer to get to the maximum volume. And then if we have the large marble chips, and again we are seeing what we'd expect to see, you're getting smaller volumes at these timed intervals. The reaction is going slower, and in fact in the 180 seconds it doesn't actually reach the maximum volume. If we had more time and we kept timing it, it would get to 40 and then it would stop. But this reaction takes longer than the time we actually measured it for. So what we're going to do is plot this as a graph, because that is one of the key skills from this topic, is the graph skills. That is the plotting of graphs, the interpretation of graphs, and the plotting of graphs should be easy marks, 3 or 4 easy marks. So we're going to start off with the axes. So what's changing and what's being measured. So what's changing is the time. So this is our x-axis. What's being measured? The volume of gas. So that's our y-axis. And what we actually have is the reaction being repeated 1, 2, 3 times. So we're actually going to have 3 plots on the same graph. So our x-axis is time. So we need to get a maximum of 180 along this x-axis. So we've got 1, 2, 3, 4, 5, 6, 7 large squares to do that in. So 180 divided by 7 is 25.7. Now we're not going to go up in 25.7 intervals because that's a ridiculous scale. We can't round down because that's the minimum we can do, so I'm going to round that up to 30 and go up in 30s. So 0, 30, 60, 90, 120, 150, 180. And by doing that you assure 2 things. Number 1, that you're not going to run out of space, you're not going to go off the graph paper, and number 2, you're going to use the maximum amount of the graph paper. And our maximum value for the y-axis is 40, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares to achieve that in. So 40 divided by 9 is 4.4, so I'm going to go up in 5s. So we have time in seconds, and we have volume of gas in centimeters cubed. So we need to plot this data then. So let's start with the small. So after 20 seconds it is 10. After 40 seconds it is 20. After 60 seconds it is 27. After 80 seconds it is 34. After 100 seconds it is 38. And then at 120 it is 40. At 140 it's still 40. At 160 it's still 140. And at 180 it is 140. So there is our small marble chips. Our medium marble chips, so at 20 it is 8. At 40 it is 16. At 60 it is 23. At 80 it is 28. At 100 it is 32. At 120 it is 40. No, sorry, at 120 it's 35. At 140 it's 37. At 160 it is 39. And at 180 it is 40. And then finally, for the large marble chips, at 20 it is 5. At 40 it is 10. At 60 it is 15. At 80 it is 20. At 100 it is 23. At 120 it is 26. At 140 it is 29. 160 it is 31. And at 180 it is 33. So we've got 3 different plots there, and they're all going to go through 0, 0, because at time 0 the volume of gas produced will be 0. So if we just get a pencil, always do your line of best fit in pencil. So we're going to have 3 different lines of best fit here. We're going to have the, I'll start with the large because that's going to be the easiest one to draw. Okay, again, practice your line of best fit. It needs to be a smooth, continuous line. It does not need to go through every single one of the plots, okay? And then I'm just going to label it. This is our large marble chips. Okay, and then we're going to do our medium marble chips. Practice the line a few times. Want a nice, smooth, continuous line. Okay, that is our medium marble chips. And then our small marble chips. Again, practice the curve. This one's going to be a bit harder to do. There we go. And there is our large marble, our small marble chips. So, what can we see from these curves? Now remember, we've got volume of gas and time. Neither one of these is rate. The rate is the gradient of the line. So the rate is equal to the gradient. So, when the gradient is steeper, the rate is faster, and when the gradient is shallower, the rate is slower, and when the gradient is 0, then the rate is 0. So what we can see is that the small marble chips has a steeper gradient, so it's got a faster rate. The medium marble chips has a shallower gradient than the small marble chips. It's got a slower rate, but that is steeper than the large marble chips, so it's faster. The rate is greater. You'll notice that they are all steeper at the beginning and they all get shallower, so the rate is getting slower over time, which is common with most reactions, because over time the reactant particles are being used up, they're becoming products, which means their concentration is decreasing, which means the frequency of their collisions decreases, meaning the rate slows down and decreases over time. And what you'll also see is that as soon as the gradient is 0, the reaction is finished, the rate is 0. So for the small marble chips, the reaction finishes here at 120 seconds. The medium marble chips, the rate keeps continuing and doesn't end until here, 180 seconds. And the large marble chips doesn't finish. We would have to time for more time intervals, before we could find out when the large marble chips ended. This reaction was still occurring when we stopped timing it at 180 seconds. So we need to think about why this is happening. Why do the small marble chips react faster than the medium marble chips, and why do they react faster than the large marble chips? And it all comes down to collision theory. Now, we need to remind ourselves that collision theory states that reactant particles must collide with enough energy to react. Okay, so anything we do that increases the chances or frequency of collisions will increase the rate, and anything we do that increases the energy of those collisions will increase the rate. So let's have a think about what's actually occurring. So in each one of these, we used 10 grams. We had 10 grams of small marble chips, we had 10 grams of medium marble chips, we had 10 grams of large marble chips, and they all were reacted with the exact same volume of hydrochloric acid and the exact same concentration of hydrochloric acid. So the only difference between them is their surface area, from being small, medium or large. So let's have a look at this excellently drawn diagram. So I've got two 10-gram samples of calcium carbonate. I've got one as one large cube and one that's been broken up into smaller cubes. Now, when we are dealing with reactions, remember the first thing that needs to happen is the particles need to collide. So each one of these is surrounded by acid particles because we're dropping them into hydrochloric acid. So we'll just draw the hydrochloric acid particles around it. And these hydrochloric acid particles need to collide with our calcium carbonate particles. Now, they can only collide with the calcium carbonate particles that are on the surface. So if we have more surface area, we have more particles on the surface, so there are more calcium carbonate particles that the hydrochloric acid particles can collide with. So if we look at this, they can collide with the ones on this surface, on this surface, on this surface, and obviously on the ones you can't see on the other side. Whereas if we break it up into smaller pieces, you increase the number of surfaces that the hydrochloric acid particles can collide with. And we could do a very simple sort of mathematical calculation to show that increase in surface. Okay, so now all of these bits here, actually I'll do this bit in red. This surface here wasn't visible before. Neither was this one here or this one here, or this one here, and there's a bunch of them you can't even see because of the angle we're looking at it. But everything that I'm shading in red here wasn't previously accessible. The hydrochloric acid particles couldn't have collided with them because they would have been on the inside of the cube. So we've now increased the surface area. So our hydrochloric acid particles now have more surface particles that they can collide with. And collision theory states that if you increase the chances or the frequency of collisions, then you are going to increase the rate. So let's have a quick look at this then. So we've got 10 grams of calcium carbonate in both. But if we look at their surface area, well, to work out the surface area, you need to know the cross section. You need to know the area of one side. So for this one here, it's 2 by 2. So 2 times 2 equals 4 centimeters squared. And how many sides do we have? We have 6 sides, giving us 24 centimeters cubed surface area. Okay, now let's look at this calcium carbonate. Now each one of these cubes individually has a 1 by 1 cross section. So each face is 1 by 1, okay, which is equal to 1 centimeter squared. And each cube has 6 faces. But now we have 1, 2, 3, 4, 5, 6, 7, 8 different cubes, giving us 48 centimeters cubed. 48 centimeters squared. So we've got double. Okay, just by breaking this up, you've used the exact same amount, 10 grams of both, but just by breaking it up into smaller pieces, I have doubled the surface area. Okay, so in terms of collision theory, increasing surface area increases rate of reaction, because there are more surface particles to react, because remember, it's only the particles on the surface that are able to collide. All the particles on the inside of this cube can't react until the ones on the surface have reacted. So if we increase the number of surface particles, we're going to increase the frequency of collision. So this increases the frequency of collisions, therefore increasing rate. And remember, this only applies when you have a reactant that is a solid. Okay, so temperature affects more or less all reactions. Concentration is relevant when we are dealing with aqueous solutions. Pressure is relevant when we're dealing with gases. Surface area is relevant when we're dealing with solids. And we need to be able to justify all of these in terms of collision theory. Are they increasing the frequency of collisions? And how? Are they increasing the energy of those collisions? And how? And we need to use that to justify why they're increasing or decreasing the rate of reaction.